Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. You may have noticed the title for this session is a Beginner's Corner, Discovering the Value of EasyPower PowerFlow. And my initial slide there was talking about just how to do a PowerFlow with ArcFlash database. Frankly, there's kind of a combination of the two topics that we want to cover today. Appreciate your attendance, and certainly if you have any questions along the way, feel free to enter them. We like to start each session with a poll question, and so we appreciate your participating as we do that. Today's poll questions are aimed at PowerFlow related topics. So specifically, how often do you conduct a load flow? And this is applicable whether you're a facility or a consulting firm. So just to get some initial feedback, again, no obligation, but it helps direct some of the presentation. And here's how folks responded. And here's our next question. When you start a PowerFlow study, does it usually involve starting with the ArcFlash data file? Now, as you can maybe guess, part of my methodology here, and I appreciate your participation, we'll leave this open for another 5 seconds or so. Part of this discussion is talking about value and justifying, if you will, how EasyPower fits into that conversation. So here's how folks responded on this question, and this is the question I guess I'm primarily going for, and that is how does this all fit together in terms of value from both directions? So to that end, I want to talk about viewing the same situation from each side, and that is from a customer facility side and from a consulting firm or a contractor side, where both parties have maybe had an engagement specifically on ArcFlash, and then may or may not have reasons to talk to each other along the way. So what I'm going to be touching on here real briefly are some industry trends and how I think that pertains to the value proposition that, in my estimation, is the way of the future. And one of those venues or one of those potential connections is better utilization of the tools that are available in the market. So let's jump into it and talk about it. So this is a 2013 survey of jobs in the engineering field, specifically in power systems, technical fields. And bottom line, there is some migration of the functionality of facility engineers or power systems engineers in terms of the workforce replacement, and about half of the workforce is going to, during the next 10 years, is going to be turned over, if you will. Some with respect to retirement, and some with just basic attrition. But basically half of that is expected to be turned over. Projections from, again, this is from the Center for Energy Workforce Development, are projecting that in the 10 years from 2010 to 2020, there's roughly an expected requirement of 33,700 some odd total personnel in the technical field. And this includes, line workers, technicians, operators, and engineers. And if you look at what's coming out of the schools and universities, there's a projection that roughly an average of anywhere from 2,500 to 5,000 graduates per year are expected, which roughly equates to the numbers that are being expected to be anticipated as far as requiring replacement. Well, if you look at what the Bureau of Labor Statistics says, they anticipate relatively small growth in the EE requirements for power systems engineering, specifically power systems engineering. And they're expected to see more companies cutting costs by contracting engineering services. So while there may not be a lot of organic growth, there's certainly a need for replacements. And the bottom line is many of the functionality or the job function requirements that have been part of corporate facilities and corporate manufacturing is moving into outside sourced engineering firms. So again, the jobs are still going to be filled, but they may be filled by third-party contractors and the like. Well, then you might say, how does EasyPower fit into this discussion? And the point that I would like to make is that there's going to be a need for increased productivity any way you look at this. There's still a growing demand for the services, the products, and productivity, even though the labor supply, the labor base, is not really going to be growing all that much substantially. And due to the fact that the functionality is moving outside of the corporate responsibility or reporting structure, I maintain that there's a need for increased communications and more efficient communications. And one of the case in point, in my humble opinion, is the PowerFlow capability and utilization, because the arc flash restrictions or regulations from the government bodies or regulatory bodies is requiring a fair amount of data be maintained at some point regarding manufacturing plants. So EasyPower, so the bottom line is, if you and your client are both able to communicate in an EasyPower format, there's a higher potential that you will have a better coupling, a better communication link with that customer. And every time we've done a study side by side between the EasyPower tools and comparable tools, including operators with the same skill set or same experience, we were able to document a 30% faster or improved throughput in doing specifically arc flash studies. So the bottom line from this train of thought is, if you're a facility owner, even if you have someone else do your arc flash study, request that the database be part of the deliverables. The other side of the coin is, if I'm a consulting firm and I'm doing a arc flash study for a client, there are advantages, and I am better served, as well as he is better, or they are better served as my client, if I share that database with them for a number of reasons. So recently I took a poll during one of these webinars asking how frequently clients or customers do PowerFlow, and it was roughly 50-50 as far as how often or whether or not PowerFlow is being included in a facility platform. But on the other hand, how frequently consultants share their database with their client is preponderantly no. In fact, the data is not shared. So I might make the argument both ways. If I take a con position, whereas, well, I don't provide it, the client does not know, it may not know that the database even exists or how important it is to him. And if his primary objective is to update the arc flash study every 5 years, what are the chances he's going to go to someone else for that study, not knowing that the database already exists? His goal is going to be reduce cost, and if I'm able to share that data, or if he has that database, he has the ability to reduce his cost for a follow-on study. The zinger on this particular set, though, is if the client learns that you have the file and it's information that is valuable to him, what does that mean about your communications and your engagement with that client? On the other hand, if you do provide it and both you and your client have the ArcFlash study file, the ability to do changes, the ability for him to make modifications relatively small if necessary, and maintain his compliance for NFPA 70E can actually be enhanced, but that gives him the ability to communicate with you because now he may have changes in his database that he's understands the need for you to have that update included in your file. So I frequently reiterate this mantra, and that is the EasyPower tools will not make you a power systems engineer, but they will make it increase your ability to communicate with a power systems engineer, sometimes many times over. And the fact that the tools are more productive for a consulting firm and easier to use on a less frequent basis as a facility engineer, I don't need to be a power systems a power user of the tools to be able to convey and understand the communications link that I now have with my engineering resource. So the bottom line is, in an ArcFlash study, what we're really looking at is the worst case scenario. What is the worst possible fault that my system could be subjected to, and will my system elements and the equipment in the plant survive that fault, and to ensure that any protective device that's installed is properly adjusted and will activate to protect both the equipment and personnel if the worst case happens. Now, if we look at what it takes to do a load flow study, the difference is we're looking at normal operations. And that includes the ability to anticipate or predict voltage fluctuations due to loading changes, due to aging changes, due to some sort of maintenance issues, likewise environmental variations. Load flow might be something that we would want to incorporate both in terms of our utility spin, whether or not we have power factor issues, whether or not we have motor start fluctuations that could be causing flicker or interference with other system operations that aren't necessarily obvious and could be actually obscured by some of the control systems we have in place. So again, this is what if, but it will vary based upon any particular installation or client. And frankly, if you look at the fact that my client's capabilities, both in expertise and sophistication in terms of engineering resources, he more than likely will be needing a engineering resource that he's very closely coupled with. So that's my kind of bottom line here. Now, in terms of load flow itself, it's actually something that's valuable in a number of respects, but seldom is that value based upon one particular snapshot. And so more often than not, to be of value, you want to be able to track changes in the load flow, and that might be considering trends of operations that incorporate multiple configurations, both of my system and operations over time, and loading requirements. So there are a lot of reasons to look at a load flow as an ongoing dialogue, and the ultimate benefit will be something that's a continued communications rather than a one-time event. Now, frankly, that's not something necessarily I need outside engineering resources to do. It could be a system that I set up for my plant with maintenance operations doing most of the data collection, or even in some cases automatic data collection due to my system controls, but being able to interpret what those data points are telling me is where I need to be able to communicate with resources that may have more capability than I can support on a full-time basis. So what we can look at when we get into the EasyPower tools, we can look at the load changes throughout the plant and how it affects other parts of the system. There may be a need to keep an eye on power factor correction. Frequently, just the ability to, in many parts of the country, power factor can be a significant penalty in terms of utility charges, because if we have times where our power factor is beyond a certain limit, we can receive a significant penalty, a demand penalty, that can easily justify the need for monitoring and PowerFlow studies. Again, optimizing transformer taps, being able to track and anticipate peak load conditions. Seriously, if we have a cogeneration situation or even a microgrid situation, arc flash is not going to tell us too much other than that worst case scenario, whereas having an ongoing trend analysis or status of power flow at different cogen plant operations could be extremely valuable. It's also a good way to anticipate plant expansion and to verify what the effect would be on our utility spend or our installed base of equipment if we expect to put on additional capacity or move equipment around within the plant. Likewise, anticipating the operations of emergency generators, or being able to go through a what-if scenario if we have equipment failures or outages and how that would affect plant operations. Likewise, being able to track how the impact of utility systems variation over time and seasons can be anticipated and predicted utilizing load flow, giving us the ability to anticipate or prepare for contingency operations and determine whether or not our generation capacity is going to meet the need. Again, we talked about power factor studies, system losses, and then finally, what I'm going to do is get into some of this stuff starts to become very specific to my operations, and the answer is there's a serious amount of data that can be extracted from a load flow for my particular plant once I take into consideration what the needs of my plant may be. So here's the basic problem, if you will, or the power flow equation. Is the power drawn by load varies with voltages. The voltage will vary with the load itself, and they become interdependent. And it's this interdependency that makes the load flow problem relatively tough to do by hand. And so we're talking about the solution of simultaneous equations. And ultimately what we're looking at is the ability to utilize the real power to do work and understand whether or not we have a demand for reactive power that ultimately provides that capacity to us, and that relationship is referred to as the power flow triangle. And again, this is fairly common. It's a solution in the fact that it varies on a fairly frequent basis that makes it nice to have a computer system that can do these calculations for us. So in terms of the power flow versus how the system was designed, primarily there's a fair amount of conservative yard banding when you're looking at load calcs by the National Electric Code. And you can recognize this when you talk to a utility company about what they provide generation-wise when you approach them with a specific design requirement for a new plant. And so you'll find that the utility company will supply much less capacity than the NEC may require that we design to. So power flow is generally based on expected actual loads, And getting into the details of it here is what the advantage of going through this operation or this discussion with an engineering resource. So bottom line is we run PowerFlow, we compare the bus voltages and branch voltages, which we take multiple times, and this can be installed monitoring, it can be portable or manual data collection, or it can be data loggers that we put around the plant. But we want to identify where there's a discrepancy between the predicted voltage and current flows and what's being monitored in our actual plant. And so over time, as we record these voltages, it gives us an opportunity to have multiple touches and multiple communications with our engineering resource and extract additional benefits from the tools. So I'm going to jump into a couple examples of this. And again, it's relatively straightforward. The bottom line is that the tools make it relatively easy to go through this process. And so the advantage is setting up the procedure to do the data collection and then routinely incorporating the results of that data collection into what my model is showing. So here we're showing meter data on a distribution feeder system that shows peak kilowatt and peak kVR at this point in my system. If I go in and do a PowerFlow analysis based upon my nameplate data, I can show that my loads are consuming, in this case, 471 kilowatts. And if I go back and look at my PowerFlow options, I can see that my units on the loads and the kVA are both in kVA and power factor. So I want to put this into real and reactive power. And as I do that, I can see that this load is 401 kilowatts and this reactive power is 248 kilowatts. So having measured this, I know what I need to estimate in terms of the other loads in my plant. And I've represented that by just a basic load. So to do that, I'm going to do a little math here, which I can't do in my head. And we're measuring the 1.43 kilowatts. And we're actually registering on the motor usage itself, 0.401. So that means this other load's probably going to be a little over a megawatt. So we can go in on a temporary basis and enter my 1.09. So let me put in that as my temporary data for the real power. Then for the reactive power, I'm measuring 0.82 and I'm measuring 0.248. So let's make that inclusion. And so this is the initial data point, and over time I'm going to take additional measurements and effectively find the trend line of any changes in the system. And when there's not 0.572. When there's not alignment, then I start to look for the discrepancies. Okay, so now what I'm in a PowerFlow solution. I'm showing my total loads down here to somewhat match my measured for peak kilowatts and kilovars. And I can see that it's less than what my utility is indicating. If this number it matches what my utility bill is coming in at, then I obviously have losses in the system. And EasyPower tools can give me where potentially that could be taking place. So transformers can be a location for loss generation, in which case we would show transformer losses. In this case, it looks like it's about 13 kilowatts reactive power, 13 kilowatts real power, and 91 kilowatts of reactive power. Now, if this was an expanded system, I'd have more opportunity, and The tool gives me the ability to look at the voltage taps, the generator and load, draw and demand, and configurations. And we can project that both in real and reactive power, as well as current kVA and power factor. We can look at the transformer taps, voltage drops, in which case we're looking for voltage drop basically caused by the loss, and we find the same thing across cables. All right, so this is a relatively simple example. Let's try one more. Same type of thing, where we measure some data at the major switch gear. And as we go into PowerFlow, we can look at our load system. And again, it looks like we're set up for kilowatts and megabar. Megabars and megawatts. And our losses are in kilowatts and kilobar. All right, so we're going to do the same thing. We have a total kilowatt delivered of 1.43 megawatts. And so we're going to divide the balance of any remainder between the three branches. And again, you condition this with more intimate knowledge about the system, and therein lies the advantage of having the facility engineering team or maintenance team involved in the discussion. So we have 1.43, and we'll subtract 0.401 and 0.207. And so there's a difference of 0.822 if we're going to divide that equally between these three distributed loads. I'll just divide this by 3. We want to put 0.274 at each of my loads. So on a temporary basis, I'm going to put 0.274 in each of my fixed loads. And we'll do the same thing for the reactive power. Now again, over time, I want to reassess this and look to see where there's changes and balance that against the variations for either seasonal discrepancies or seasonal changes, load changes, capacity changes, and verify that my losses, as they're identified, can be explained, because it's where we have a discrepancy that we can focus either preventive maintenance, preemptive elements such as coming in and doing an infrared scan of equipment in a branch that appears particularly lossy, because it could be poor connections, it could be poor elements, it could be insulation wearing down. There's a number of elements that could be causing the problem. So we want to take out the reactive power of 0.8 and subtract 0.249 and 0.155 and divide that by 3 to spread it out. So I'm going to add 140 to each of my distributed loads. Now, obviously, once I get the system set up, this is something that my maintenance personnel could do on a procedural basis or as frequently as I want to collect the data, and then have a review between my engineering team and my facilities team to talk about the impact of what these results are showing and what modifications need to be made in my system going forward based upon what capacity changes I need to take. So now we can look at my utility supply. So again, we're showing utility with a power factor correction with a power factor of 0.951. No, that's reactive power. Let's see what's happening with my power factor. Yeah, so I'm showing on the utility supply, my power factor is less than 0.85, which could, in certain parts of the country, suggest that we may get a demand penalty from the utility company. Likewise, we can look at branch flows. At some point in time, I may want to be able to go out and make measurements at each of these branch conductors or panels and balance that out or incorporate those differences to better refine what my PowerFlow results are. So the bottom line here is that this is not a standalone situation. This is very much a procedure that suggests if I'm going to be outsourcing my engineering functionality, I need to have regular communications on a platform that not only can I understand, but my maintenance people can utilize for sometimes day-to-day operations. So frankly, we're just barely touching on the capabilities of the tools themselves. For instance, if we wanted to look at voltage losses, we can see what the losses are across the transformer and across each of the cables. And where we're finding discrepancies there, we'd want to go back and understand the source. And this is the losses per branch in real and reactive power. Here's any overloads that I have. So clearly here, I'm within 10%. And this is a control system I've set for to flag my overload and under voltage thresholds. And again, this may change based upon the season. So it may be something I'm concerned about, or it may not be something I'm concerned about. Again, the more knowledge I have, or the more information I have, the more data I have, the more intelligent the decisions I can make. And then voltage violations. Looks like we're not having problems with the voltage at this point. Okay, so that was what I wanted to cover, and I appreciate your patience. Let's see if I'm going to touch on. So the bottom line is companies will grow to depend, I believe, more on engineering firms in the foreseeable future, quite easily in the next 5 to 10 years, much more so than we see even today. And it's the firms that are able to develop a proactive dialogue and a more efficient communications scheme with those engineering resources that will help them succeed in terms of reducing their spend for maintenance and repair and down system line down. So by maintaining the model and developing a system to do trend analysis and correlate that with the information that the maintenance team is seeing, our costs can be decreased. Thank you very much for attending today. Any questions that are submitted we'll answer via email. I encourage you to check into EasyPower.com because we have recent announcements for new regional training in Austin in March and in Portland, Oregon in September. And we now have the ability to provide online regional training that has been announced on the website. And just one quick reminder, we do have in the Dallas-Fort Worth area here this month an arc flash workshop, and next month we'll have one in Portland. Thank you all. Have a good week, and we'll talk to you during the next refresher.